Hello, Mr. Davidson. This is our physics in the movie project. This is by me, Aaron, and Oshin. This is the clip we'll be using for reference throughout our presentation. It's gonna be fast and furious. Okay.
The length of the race we calculated from where they were starting at the light on the left side, on the bottom left side, and then the ending, which we put at the railroad, which is 440 meters or a quarter of a mile. The vehicles involved, this is the black car, which flipped in the air. We used 4,000 pounds because that is or 4,012 pounds because that is the model that was used in the filming. This is the truck that was used, and we used 18,000 pounds as the weight. The duration of the race, we started at, we realized that the race stops at 2 minutes, and the race does not start until 38 seconds in. Within these 2 minutes, there's about 55 seconds of time where the video cuts away from the race, which we subtract 38 and 55 from 120, and we end up with 27 seconds. So the measurements we used, car mass as 1,820 kilograms, distance as 440 meters, and time as 27 seconds. So we calculated for the time, which is 27 seconds, and we found the distance. So we used the distance formula to calculate the acceleration, which is 1.2 meters a second squared. The velocity, because they start at a rest, the velocity initial is zero. And to calculate the velocity final, we use the acceleration times time, which we calculated to be 1.2 times 27, which is equal to 32.4 meters a second.
And we can apply these things when we look at Newton's laws. So we can also calculate the net force and in according to using Newton's second law, which is force times mass times accelerate force is equal to mass times acceleration. And so but first we can find the force of gravity by using the acceleration in the y times the mass. And when we do that, we would find it to be 18,200 newtons, which would also be equal to the normal force. Um, and when we're looking for the net force after this, all we would need to do is find the mass in the or we would need to find the mass, and then we multiply it against um the acceleration in the x. And we found the acceleration in the x earlier be 1.2. When we multiply that by the mass, we get 2,184 newtons as the net force. And I have drew a free body diagram so you can see the force enacted on pushing the car forward, and the normal force in the opposite direction is the force of gravity. And then we can also apply Newton's laws when we are finding the kinetic and static friction. And while looking for the mu, which is important part of it, we found that the static friction coefficient or mu is usually higher than the kinetic coefficient of friction. The static coefficient is zero point 0.9, which is what we used on average. And so when we're finding the force of friction that's static, all we would need to do is multiply the mu times the normal force. And we're looking for the normal force, which we found earlier. It would just be 18,200 newtons. And then when we multiply it against zero point 0.9, we can find the frictional static force to be 16,380 newtons. And when we're looking for the kinetic force, it is very similar. It is just again just the mu times the normal force. The only difference is that we are using a different number for the mu, because again the kinetic coefficient of friction is usually lower than the static friction because it's already in motion. And so when we multiply zero point 0.8 times 18,200, or the mass or the force of the normal force, we would get 14,560 newtons as the force of friction that is kinetic, or otherwise when the car is in motion, which I illustrated here in the free body sketch. I pointed out that the frictional force that's kinetic only applies when the car is in motion. And as you can see in the other free body diagram, I have the force of friction when it's static without the motion arrow. And another thing, an additional topic that we chose to implement that was in our video was when the car collided, which you saw in the clip, we could find the momentum and the momentum and the impulse. And to find the momentum value, we would just multiply the mass times the change in velocity. And again, we have the mass and then the change velocity. Um, it would be the final velocity minus the initial velocity, but we know that the car started from rest. So we would really just need the final velocity. And we multiply that times the mass, we would get 58,968 kilograms times the mass over seconds. And when the car is colliding with the truck, it takes about zero point 0.4 seconds for the car to stop and change its direction. And so we could calculate the newtons that were enacted on the car by um when we use the momentum value and the change in time, or the change in time. And so when we divide the momentum by the change in time, we could find that the force enacted on the car was 147,420 newtons, which makes sense because there was a large damage and the car was no longer able to run after it crashed. And here you could see the free body diagram. It has both the impulse value that is going towards the truck and then the impact that the truck's force is pushing back on the car when it collides.
Our uncertainty and error analysis, because of how many cutaways and overlapping clips there are on the video, where it cuts from racer 1 to racer 2, we could cut down about 61 seconds, along with the 38 seconds until the start of the race. So it could be up to 21 seconds that the race would actually be. Due to this change in time, to be able to reach that speed, their velocity would change. So their velocity final could be up to 51.3 meters a second because of this increase in acceleration. And the different cutaways led to more speeding up.
Thank you.